Good morning, welcome to new lecture. Today I will solve several problems. In order to learn this problem very well, please first look at the problem statement. I will explain problem statement first. Then try to solve yourself. And regardless your solution is right or wrong, no problem. First try to do yourself. After that, what's my solution? In that case you will learn better. First example, we have this frame. We have, let's say draw the picture from beginning even. That will be better. First example, we have a frame here. This is roller support. This is in support. We have member here. A, B, C, D, E. This length is L. From here to here, totally it is L. At each side it is L over 2. We have concentrated load here. We want to find internal force in member AC. So we have this frame. This frame is subjected to concentrated load. At midspan, we want to find internal force in member AC. First step we should find reactions. In order to find reaction, for example, EY. How much is the EY? I can take moment respect to point A. EY times L minus P times L over 2 is equal to 0. Summation of moment respect to A. EY times L minus P times L over 2 is equal to 0. From here you can find EY is equal to P over 2. So summation of forces in vertical direction is equal to 0. AY plus EY is minus P is equal to 0. Summation of forces in vertical direction is equal to 0. So AY plus EY minus P is equal to 0. From here you can find AY is equal to P over 2. Summation of force in horizontal direction is equal to 0. There is no force in horizontal direction. This one will be 0. Now I want to find internal force in member AC. It is very easy to find. Assume I will cut like this. I will keep right side. This is FAC. This angle is theta. We can find that. I can take moment respect to point B. I can write summation of moment respect to point B is equal to 0 for right side of structure. In that case, I will have EY times L minus P times L over 2 minus FAC sine theta times L over 2 is equal to 0. We know EY is P over 2, so it will be P over 2 times L minus PL over 2 minus FAC sine theta times L over 2 is equal to 0. From here these terms they will cancel each other, so FAC will be equal to 0. This is one way to solve it. Another way you can look at the free body diagram. At point A, at joint A, you have this force FAC, you have this force FAB, and you have reaction here P over 2, and this angle assume it is alpha. Summation of forces in horizontal direction is equal to 0. If you decompose FAC in horizontal direction, will be FAC sine alpha. There is no other force is equal to 0. So FAC will be equal to 0. Let's look at the next one. Next example. Again, we want to find internal force in one member. Let's look at the structure. It is one square shape. So point A, B, C, D, E, and this is L. From here to here again it is L. We apply tension force here at point E and at point A. We pull from point A and E. So what is internal force in member F, B, C? Okay, let's look at to see how we can find this one. This is again a very simple problem. First, let's look at to these members one by one. From statics, we know force in member CE should be equal to 0. If CE is 0 member. We know this from statics. Why? Because if you cut this joint, two members in the same direction, one member is perpendicular and there is no force, external force at the joint. So the third member internal force will be equal to 0. Or if you look at the free body diagram, if you cut joint C, look at the free body diagram. If you write summation of force in horizontal direction is equal to 0, so FCE will be equal to 0 because there is no external force in that direction. So if that is equal to 0, I can remove that member. If I remove that member, what will happen? If I remove that member, we will have only members in the DC member and CD member in this direction, perpendicular to the P direction. Assume we don't have these members. Assume we don't have these members. If we apply this force, what will happen? If we pull like this, it is very clear the joint D will move down, joint B will move up, and it will deform like this. And the distance from A to E will increase. So, if we remove those, we will have unstable structure. And in this square, joint A and D distance will increase and joint B and D distance will decrease. Here, from symmetry, we can understand if we apply P and P here, this will be in equilibrium. From symmetry, we can understand that if we have a square shape, I pull from both sides with P and P. If I apply another P and another P upward and downward, this will be in equilibrium. So FBC force should be P. The force in BC should be P and negative P. It will be under compression. But you can, if you cannot figure out that, you can use joint method and solve using joint method. So, you can first cut this joint, write summation of force in horizontal direction and vertical direction. From symmetry, the force in AD and AB should be equal. If you write summation of force in horizontal direction, and because you have this angle, it is 45, it is, because that angle, it is 90 degree. We have that angle, it is 90 degree. If we decompose in the horizontal direction, so FAD cosine 45 plus FAB cosine 45 should be equal to the P. So you can find force in this member and in this member. From symmetry we know this member and this member force will be equal. So in this joint, if you cut and write again summation of forces in vertical direction this time, you can find internal force in member BC, and that will be equal to negative P. So those very simple problem, and with only statics course knowledge you can solve those. You don't need anything else. Let's look at the next one. Next problem, again it is one frame. You have this frame. This is hinge, 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 fixed support, and this is rigid joint. A, B, C, D, E, F, G, H. 3 feet, 3 feet. 2 feet, 2 feet. We apply force here, it is 2 kips. We want to find moment at node or joint B from member BC. So we want to find how much moment we will have at the end of member BC. So let's see how we can approach this problem. Again, this is very simple problem. Why? Let's look at this part. If we don't have this member, what will happen? We have 3 hinges in the same level, 3 hinges in the one direction. So this is unstable system. There is no stiffness for this system, EFG. So if we apply force here, this will deform like this. Point F will move down. So part EF and FG contribution from this load 2 kips is 0. Because if we remove this member, this part, it is not a stable part, it is unstable part. So these 2 kips will transfer only to this member. This member force will be 2 kips. Now I can delete this part. So 2 kips will transfer totally to this member. Here we have 2 kips. Now, the CD part, hinge, hinge, and here we have support. You see, this part again, it is unstable. It will fall down like this. So the contribution of CD part, again, it is 0. Entire this 2 will transfer to member BC, because this joint is rigid joint and BC part, it is a stable part. So what is the moment now? at point B. Moment at point B will be 2 times distance. 2 kips times 3 feet. So moment here will be 2 kips feet. And the moment direction will be clockwise, and it will create compression underneath of this, so it is negative moment. So the moment will be, 2 times 3, 6 kips feet, load times distance. Load is 2 kips, distance is 3 kips. 2 times the length of BC, because load and BC, they are perpendicular to each other. 2 times the distance 3 will be 6 kips feet. Moment at the end of BC member. Let's look at to the next example. Next example, it is this example. Point A, B, C, D, E, F, G, H, I, and these distances are L, all of them are L, 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 and in this direction again they are L. External load is here, P. Problem statement says determine moment traction at support I. We want to find moment traction at support I. How we can find that? Let's look at this system. What is happening? We are applying point load P at joint D. If I cut this here and I remove this part, let's look at the equilibrium of that part. If I cut this part, what is happening? I will have one reaction in horizontal direction, another reaction in vertical direction. Let's say I show this with Gy, this is Gx. If I cut through hinge G, if I write summation of moment for this top part respect to point C, what I have Gy times 2L minus P times L is equal to 0. So I have Gy times 2L minus P times L is equal to 0. From here, Gy will be equal to P over 2. Now, if I take moment respect to this hinge for this part of the structure, what I will have? I will have Gy times L minus Gx times L is equal to 0, because moment at hinge is equal to 0. So I can write Gy times L minus Gx times L is equal to 0. Gy, it is P over 2, so Gx will be P over 2 as well. So this will be P over 2. Now we found the reaction at joint G. So we can change the direction of those reactions. That will be action applied by left side on right side of the structure. So I can remove entire this part totally, and only I apply the forces that left side applies to this part, that will be P over 2, P over 2. And pay attention, those directions we found, they were reaction, so these are action force. It should be in inverse direction, only we will sense the direction. Now, what is the moment at point I? If I take moment respect to I, what I have? I will have mi minus P over 2 times L, mi counterclockwise minus P over 2 times L clockwise plus P over 2 times L counterclockwise is equal to 0. I'm taking moment respect to I. mi reaction counterclockwise minus P over 2 times L. It wants to rotate this part clockwise, so negative respect to point I. P over 2 times L, it wants to rotate this piece counterclockwise respect to I, so positive is equal to 0. These, they will cancel each other, and my will be equal to 0. So sometimes the problem statement, even in real design problem, sometimes problem is it seems very complicated. You see huge structure, it is a little bit scary, but be patient, look at the structure in details, try to communicate with the structure member so you can simplify that structure. You saw this structure, it was a little bit big, but nothing is here. We can simplify that and we can solve it. It is a very easy problem. Let's look at to the next one. Next problem. We have this one. Two feet, 4 feet. We have force here, 3 kips. A, B, C. Problem statement says determine the deflection at left side of joint B. We want to find deflection at the left side of joint B. How we can find it? First, let's look at to the reaction Cy here. What is reaction Cy here? Reaction Cy here is very easy to find because you see this joint. In this joint, right side and the left side, they can move respect to each other in vertical direction. So it will not transfer shear force from left to right or right to left. So if I write summation of forces in vertical direction is equal to 0, Cy minus 3 is equal to 0, because this part will not allow to transfer any shear force from right side to left side. From here, Cy minus 3 is equal to 0, so Cy will be equal to 3 kips. Now let's see what is the moment at point B. So if I take moment respect to point B, I will have Cy times 4 minus 3 times 2 is equal to 0. So MB will be Cy times 4 minus 3 times 2. That will be equal to Cy, it is 3 times 4 minus 3 times 2. From here that will be 12 minus 6, 6. So MB will be 6 kips feet. You see Cy times 4. It wants to rotate this piece, BC piece, counterclockwise. 3 times 2, it wants to rotate respect to point B clockwise. So I can remove this part and only I apply the effect of that part. The effect of that part will be one moment in this direction, which is 6 kips feet MB. Now, if we have one cantilever beam subjected to moment at free end, what is the deflection? We can find that from virtual work method. If I have M here, what is the moment diagram for this? It will be one rectangular M. I want to find deflection at point B, so I will apply unit load here. What will be moment diagram? It will be L. From integration table, rectangular to triangle, the coefficient 1 over 2 M times L over EI. That will be delta B, so it will be M L squared over 2 EI. Here delta B will be M, which is 6, times L squared will be 4 squared over 2 EI. So this is M, one rectangular, it is right. 1 times LL, positive, positive. Rectangular triangle 1 over 2, M times L over LEI. ML squared over 2EI. Instead of M, in this example you will plug 6. L is 4 and 2, which is number EI. Any EI you have, you can plug over there. So this one was very easy problem. Let's look at the next one. Next one. We have this system, this is structure. EI, L. This part, it is rigid. Rigid means EI goes into infinity. No bending deformation. The length it is 2L. It is subjected to one distributed non-uniform load. The shape is one triangle. Here we have one hinge. Again, cantilever part, EI 2L. Here we have one member in axial direction, one column only, EA. The length is 2L. So joint A, B, C, D, E. Problem statement says I, moment of inertia for all sections, divided by A, the area of the cross-sectional area, is equal to 4L squared. Problem says determine deflection at midspan of member BC. Member BC is rigid member. We want to find deflection at midspan of BC. How we can find that? If we find deflection at point B and deflection at point C, for example, BC initially it is horizontal. B will transfer to point B prime. Any point we should find this delta B. Point C will transfer to point C prime. We should find this delta C. Then this is the rigid member. Initially it was horizontal. Then because this delta B and delta C, they can be equal sometimes, but in general case, they are not equal. So it will move down and it will rotate. So you will have one trapezoid shape, something like this. In order to find deflection at midspan here, it is easy. Delta at midspan, for example, delta, if I show with O, will be delta B plus delta C divided by 2. Because initially this BC is horizontal. Then point B will move down, point C will move down. Because delta B and delta C, they are not equal. In some special cases can be equal even. It will, in general case, it will move down and rotate. So we will have one trapezoid shape. The height in the middle will be delta B plus delta C divided by 2. Now, because BC it is rigid, we will not have any bending deformation in the BC. Initially it is straight, it will remain straight line. But only the point now, we should find delta B and delta C. How we can find delta B and delta C? Delta B, let's look at to see. This part, we apply this external load. How much load will transfer to the AB part? As much as reaction at point B. If we have one beam subjected to this kind of load, what are the reactions? What is the By? What is the Cy? We can take moment respect to, for example, B, in that case Cy times the distance to L minus area W times 2L, W times 2L times half times the distance from centroid of this up to point B will be 2/3 times the length 2L is equal to 0. From here you can find reaction here will be, you can, let's remove this part. This will be Cy times 2L is equal to, it is easy to find, even you don't need this one. You can bring to other side and simplify, but entire load, it is area underneath of this triangle. Area underneath of this triangle, it is W times 2L times half. That will be equal to WL. From WL, 1/3 will transfer to the B, 2/3 will transfer to the C. So the contribution of each part, of course, you can find using equilibrium equation. From here you can find that you will find WL over 3. Then if you write summation of force in vertical direction, By plus Cy minus entire load W times 2L times half is equal to 0. So from there you can find Cy and By. After finding Cy and By, we will not need this part. We can remove that part and apply the effect. Effect of that, it will be 1/3 WL here, 2/3 WL here, because entire load, it is area underneath of triangle. From entire 1/3 will transfer to the B, 2/3 will transfer to the C. Now, finding delta B now, it is very easy because it is very simple problem. It is only one cantilever beam subjected to point load at the free end. Delta B, we know it will be load times length cube over 3EI. So you can find delta P. Let's look at to this side. Can we find delta C? Yes, that is simple 1, 2. Why? Because it is combination of one cantilever and one axial member. In the axial member, the stiffness for this member in the axial direction is equal to EA divided by the length. If we have one member in the axial direction, the axial stiffness is equal to EA for that member divided by length of that member. EA is EA divided by length, it is 2L. We know this from mechanics of deformable body. How about cantilever beam? You know, stiffness means, I explained this before in mechanics of deformable body course. And if you cannot remember, you can watch videos I posted on YouTube in mechanics of deformable body course or mechanics of material. Stiffness means force. If, for example, we apply force P here and we find deformation. Deformation is delta. P force divided by deformation will give us the stiffness for member. For axial member, if we apply the force P, what is the deformation? If we apply force P, deformation from Hooke's law, we know it is PL over EA. So what is the P divided by delta? What is the force divided by deformation? Force divided by deformation, from here it will be EA over L. So this will be stiffness for axial member. So stiffness for this member will be EA over 2L. How about stiffness for one cantilever beam? Let's look at one cantilever beam. If we have cantilever beam subjected to load at free end, concentrated load, the delta we calculated several times will be equal to PL cube over 3EI. From here, P over delta, it means stiffness of cantilever beam will be 3EI over L cube in general case. So here, the stiffness for column, I call it K1. The stiffness for this member, I call it K2, will be 3EI divided by L. L here it is 2L, so I will plug 2L cube. Now, these two members, they deform together. You see, we attach these two members to point C, and if I apply load at point C, they will deform together. And the amount of deformation in this axial member and in this cantilever beam, it will be equal. So it means if I assume this is one spring, this is another spring, I attach these springs as parallel. Parallel, if we have several springs, if the deformation in those springs, they are equals, we will call it, we attach those springs as parallel. The springs, they are parallel. In that case, the equivalent stiffness will be summation of stiffness for each one. So equivalent stiffness here will be K1 plus K2. K1 here it is EA over 2L. K2 here it is EI over 2L cube. 3EI stiffness for cantilever beam. I prove it here. It was 3EI over L cube. So it will be plus 3EI over L cube. Instead of A, you can plug I over 4L square, or you can put I is equal for AL square. Here, you can do that. So it will simplify your calculation. From here, the delta C, deformation at point C, will be total load, which is 2 over 3 WL, divided by total stiffness. Total stiffness means equivalent stiffness for this member and this member, which is EA over 2L plus 3EI over 2L cube. So you will find delta B, delta C. After finding delta B and delta B plus delta C divided by 2 will be the deformation at midspan for member BC. Let's look at the next example. Next example, we have one continuous beam and we want to find support traction A, B, C subjected to distributed load. What is the reaction at support B, or what is the By? Because this is indeterminate system, using equilibrium equation we will not find By, because here we have, you see, two unknown here, 1 and 1. So we will have 4 unknowns. How many equilibrium equation we can find? We can write 3 equilibrium equation. Summation of force in horizontal direction equal to 0, summation of force in vertical direction is equal to 0, and summation of moment with respect to one support is equal to 0. So one unknown is more than number of equations. 1 degree is indeterminate. We should use compatibility equation. Or here it is very simple problem. We can use superposition. This is L, this is L. I can remove that support. I can apply external load. If I apply external load, this beam will deform. The maximum deformation at point B, delta B, will be 5 over 384 times intensity of the load, length, which is here 2L, entire length, L plus L, 2L, to the power of 4 EI. If we don't have support B, so this point will move down, and the amount of sagging or deflection, we can find it. But in reality, we have support over there. So if point B moves down, this support traction will apply force in inverse direction, and again point B will move up. So here it will move delta B1 down. Because of this reaction, it will move delta B2 up. In reality, delta B1 downward should be equal to the delta B2 upward, because they should cancel each other. Deflection at point B is equal to 0. What is delta B2? It will be force By times the length of the beam, 2L cube over 48 EI. If you plug these two equal, from here you can find By, because delta B1 should be equal to the delta B2. If we plug equal EI from both sides, they will cancel each other, and you can simplify more and find BY. Next example. Next example, again we have one cantilever beam. This cantilever beam is subjected one point load here and one concentrated moment at free end. This length it is 4L. This length it is L. This is A, B, C. Problem statement says find the slope at point C and deflection at point B using moment area method. Moment area method, it is easy to apply to this problem. First step, we will draw moment diagram. If I want to draw moment diagram for this beam, at point B, it is free end. If I did not have this concentrated moment, the moment was 0. Because I apply moment at point B, the amount of moment here instead of 0 will be M. From B to C, there is no force, so it will continue. After C, we have load. At point A, the moment will be M plus P times 3L. So the moment here will be M plus P times 3L, it means 3PL. Negative or positive, because this beam will deform downward. Underneath of the beam we have compression, so it is negative. If we want to apply moment area method, we should divide the moment diagram by EI. EI for this beam, it is constant, so I will divide M over EI. Here again, moment, total moment, which is equal to M plus 3PL divided by EI. If I want to find the slope at point C, the slope at point C, it means I will draw tangent to the deformed shape of the beam, and I will measure the angle with horizontal direction. So let's say show with another color. This beam will deform like this, and if I draw tangent to this deflected shape at point C, the tangent angle with horizontal direction will be the same as if I drove tangent at point C and tangent at point A, because at point A it is fixed support and tangent at point A will be in horizontal direction. These theta, they will be equal. So moment area method says the angle between tangent and deflected shape beam. If we drove tangent to the deflected shape beam in 2 points, the angle between those tangent is equal to area underneath of this diagram from point A to the point C. I want to find angle between tangent to this deflected shape at point A with tangent to the deflected shape at point C. This deflected shape beam is like this. Tangent here, it will be horizontal. Tangent at C will be in this direction. So this angle is equal to this angle if I drove one tangent to the C and another in the horizontal direction. So the area underneath of this from A to C, it will give us theta C. The area, you can calculate area over there. The area will be this height times this length, which will be M over EI times length 3L, M over EI times 3L. This height will be 3PL over EI, so plus 3PL over EI times length 3L times half, because it is triangle shape. So it will be total area from A to Z. Total area from A to C, it will give us the angle between tangent to the deflected shape at point A to the tangent at point C. So if we have deflected shape and we drove tangent at point A to the deflected shape and tangent at point C to the deflected shape, the angle between those two tangents, it will be area from A to Z. That angle, here in this example, it is equal to slope of beam at point C2, so it is easy to find theta C. Let's look at the deflection. Deflection will be from B to here, delta B. On the other hand, from moment area method, delta B respect to the A, the distance from point B at elastic curve to the tangent at point A. So the distance of point B at elastic curve, they form elastic curve from tangent at point A to the elastic curve is equal to moment of area underneath of this diagram respect to the axis passes through point B. It means we will take moment of area for this shape respect to this axis, that will be equal to M over EI times 7L, the area for this rectangular height, M over EI times 7L, times the distance from center up to here, it will be 7L over 2 plus the area for this triangle, which is 3PL over EI times 3L times 1 over 2. This will be area for this triangle. From centroid of this triangle up to here. The centroid of this triangle will be from this side 2 over 3 times the length 3L. So plus 4L. So this times 2 over 3 times 3L plus 4L. The distance from centroid of triangle up to axis passes through point B. That will give us delta B respect to A, the distance from point B, and they form elastic curve to the tangent to the elastic curve at point A, which is here is equal to deflection at point B as well. Okay, I give you several examples. I think for today is enough. So, the right way to watch these videos, first look at the problem statement, then write the problem statement, think about that and try to solve yourself. Regardless your solution is right or wrong, watch the solution and compare your solution. Thank you so much for watching this lecture. See you next session. Bye bye.